So we have a new vocab word here, differentiability, provided that f prime of a equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. So if this limit exists, we say f is differentiable at a. Now, functions can be differentiable over intervals, and so if f is differentiable at every point on an open interval, we say f is differentiable on I. So you might be wondering, where does this limit not exist? So in other words, maybe what does it look like graphically if the derivative doesn't exist? How can we spot this? Let's find out. We're going to have three cases. Actually, I'll sketch that one a little bit different. Let's say it looks like this. Okay, and this is f of x. This is x equals a. And is what we want to be thinking about right now is our derivative. F prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. Now, I know that over here we're just looking at f of x, but you could imagine that we're going to have a little bit of an issue here because we can't even, I shouldn't say we can't, but we don't even get a limit. This limit doesn't exist, right? If we come from the left, it's approaching something different than if we come from the right. So we expect that this limit down here probably isn't going to exist either. That's the idea. Let's see another situation where we might not expect that limit to exist. Let's sketch this in red here. All right, so another place is at sharp corners. So like an absolute value function, it has a discontinuity at that vertex. And again, you can see if we were just trying to take the limit of f of x as x approaches a, well, the slopes of these two lines that we have here are different. The one on the left is going to have a negative slope. The one on the right has a positive slope. So again, we don't expect this limit down here to exist. And then one more. So again, if this spot right here is x equals a, I'm actually not going to write the A in this time, but what the issue is here is we have a vertical tangent line. We have a vertical tangent line. So that's going to mean that if you were to find the slope of a vertical line, right, that slope is undefined. So similarly, our derivative will be undefined. All right, so one issue is discontinuities. Sharp corners. And places that have vertical tangent lines. Example 3, we're given the graph of f of x and we want to sketch the graph of f prime of x. One thing I want you to note about this piecewise function we have sketched here is all of the functions that make up this piecewise function, they're all linear. So let's maybe look at a little bit more general case of the derivative. Okay. Let's look at the derivative of just any linear function. We'll move over here. And actually, I'm going to write this. Let's say that f of x is equal to mx plus b. Right? That's the form that we usually write our linear equations in. Next, let's find that derivative. Take the limit as h approaches 0 of f of x plus h minus f of x all over h. Now let's replace x with x plus h. And so that's going to look like m times x plus h plus b. And then let's subtract f of x. So it's going to be minus mx minus b. And then this is all over h. And if we keep going, this gives us the limit as h approaches 0 of mx plus mh plus b minus mx minus b all over h. And you'll see maybe a few things cancel out up there. Looks like an mx cancels, a b cancels, and so all we're left with is mh over h. And I don't think we have much further to go here. We have the limit as h goes to 0 of then just m. So we're just taking the limit of a constant function that doesn't even have any h's in it. So as h goes to 0, this is just going to m. So what we found here is that if we take the derivative of a linear function, its derivative is just the slope. Let's go ahead and write that up here, and we'll use that idea as we do this example. So if you were to take the derivative of some linear function, again, the derivative is just the slope of that linear line. And let's start off with this first one here on the far left. If we find the slope of this line, remember that's just equivalent to its derivative. Okay? So m is equal to our change in y, which it looks like we go up 2, and the run we go over 2. So this first slope is just 1 here. So let's go over to minus 5. 1, 2, 3, 4, 5. And then again, our slope is 1, right? So we want to go up to right here. And this continues until we hit -3. So that'll be right here. And it actually looks like I drew both of those a little high up. Let me lower them a little bit. All right, and you might notice that I have actually left out the endpoints here. Okay, the reason for that is in order for the derivative to exist, I need, right, that limit as h goes to 0 of f of x, and actually let's take a specific point, for example here, x equals -5. So again, this limit is our derivative at 5. And sorry about that, -5. There we go. And this limit is not going to exist here at this endpoint because we can't approach from the left. Okay, there's nothing over here. And actually, the same could be said about this one. This limit, let me just change it from a -5 to a -3. Not much of a change. If we were to try and find this limit, it also wouldn't exist because as we approach from the left, it'll be actually positive, but when we approach from the right, it'll be negative. So it'll be approaching a different number, okay, as we approach from the left and right. So this limit doesn't exist. And so that's why I'm going to exclude actually all of the endpoints and sharp corners, all these sharp corners and endpoints. So let's try the next one. Let's go from the -3, 2 to 0, -1. So if we were to find our slope, again, m equals the change in y. So it looks like we go from 2 down to -1. So that means we go down 3. And it looks like we went over 3. So we have a slope of -1 here. And this continues, this slope of -1 continues until we get to x equals 0. All right, on to the next little line segment here. So our change in y, so it looks like that is 6 over our change in x, which is 3. So our slope is now 2. So we'll go up 1, 2. And this goes until we hit x equals 3. And then our very last one here, if you were to do the change in y, that'd be 0 over the change in x, which is 3. And 0 over 3 is just 0. And this will go until we hit x equals 6. All right, so this was pretty easy because our function that we started with was just composed of a bunch of linear functions. And so finding the derivative for those linear functions was really easy. It was just the slope. Okay. But we're not always going to be working with linear functions. So our derivatives sometimes are going to be a little harder to maybe sketch or even find. Okay. But we're going to go into a little bit more detail now looking at this relationship between our function and its derivative.